Okay, so we are going to talk more about intermolecular forces, and just have a look at this graph. And you may recognize this; it's in most A-level chemistry textbooks and crops up all over the place. It tells us a lot about intermolecular forces. Okay, so first of all, just draw your attention to this blue box on the right. Right, when I get a molecule, I usually think, first of all, say it was methane. I would think, right, what kind of intermolecular forces do you get in methane? I think, first of all, has it got H bonds? I realize in methane, no, it hasn't. So I realize it doesn't have the strongest kind of intermolecular forces. So does it have dipole-dipoles? Well, no, carbon and hydrogen are about the same electronegativity. And so there's no polar bonds there, no dipole-dipoles. So finally, then I come to the conclusion that the only possible kind of intermolecular forces you can have are van der Waals. Okay. So that's kind of thought process. Now, when we're thinking about the strength of these, H bonds are way and above stronger than the other two, aren't they? Now, the other two are weaker. You can't really say van der Waals are stronger or weaker than dipole-dipole interactions because the strength of the van der Waals forces depends how many electrons you've got there. So we'll talk a bit more about that later on, okay? But first of all, let's see what this graph is showing us. Right, so we've got the boiling point up here on this axis, which is an indication of the strength of the intermolecular forces. And on the bottom axis, we've got this should say this is the period, the period in the periodic table. So if we look at the red line, let's look at the purple line first of all. You can see I'm looking at the group 4 elements. So if you look at the group 4, you've got, and we're looking at the compounds they form with hydrogen. So group 4, we've got carbon, then we've got silicon, then germanium, and then tin. Right, you can see here that the group 4 hydrides, the boiling points increase steadily as you go up. Now, why is that? It's obviously because the only kind of intermolecular forces you're going to get in group 4, if you think about methane, is going to be van der Waals forces. Okay, so the van der Waals forces are getting stronger as you go down the group, and you'd expect that because they've got bigger molecular weights, got more electrons, and that's what you need for van der Waals force. You need points of contact with the electrons between molecules. So that's all fine there in group 4. Let's now have a look at what happens in group 6, which is different, as you can see. Right now, in group 6, these 3 elements, right, you get the trend we saw with group 4. You get a steady increase in boiling point. And why is that? Well, presumably because the van der Waals forces are getting stronger because you've got more electrons. But it's quite clear that water is anomalous there. Now, water, you'd expect its boiling point to be, somewhere down there, wouldn't you, if you carried on with the line? But it's not. And we know why that is. Why has water got such a high boiling point? It's because it can form H bonds, which are by far and away the strongest intermolecular forces, so the boiling point's a lot higher than you would expect. Okay, let's leave that, and let's move on to group 7. We get a very similar thing here. We get a bit of an increase in between HCl, HBr, HI, presumably due to the stronger van der Waals forces getting stronger. But HF is anomalous, it's very high, and that's because you've got H bonding in there. It's the similar situation to the group 6. Right, let's just have a little closer think about HCl, HBr, and HI. So I'm going to draw them here. Now we know that the the halogens are more electronegative than hydrogen. So they've all got a dipole, all of those molecules. They've all got a permanent dipole. Now let's think about the strength of that permanent dipole. Well, HCl is going to have the strongest dipole, isn't it? The biggest dipole. So I should say the biggest dipole. Why? Because chlorine is the most electronegative element in the halogens. It's more electronegative than bromine, which is more so than iodine. So the strength of the dipole goes up here, but the boiling point goes in the opposite direction. The boiling point increases that way. So that tells us that the predominant intermolecular force there is probably not dipole-dipole, it's probably van der Waals are more important because the boiling points do increase, even though the size of the dipoles decreases. So that's a little subtle bit which we get out of this graph. And we see the same trend happening there with group 6. Okay, which would have the biggest dipole? Would it be H2S or H2TE? Well, H2S would have a bigger dipole, got a lower boiling point, so that tells us van der Waals forces are more important there. And likewise, the green, let's go to the green, which I've had to write here, the names of them, because it's a bit messy putting on the graph. Right, this is ammonia up here, isn't it? NH3. Ammonia has got an abnormally high boiling point, and that's because you can have hydrogen bonds in ammonia, whereas in the other ones, in PH3, ASH3, and antimony hydride, there's no possibility of hydrogen bonds. There'll only be van der Waals forces there. So main takeaway from that graph then is the anomalous behavior of this lot over here, and that's because oxygen, fluorine, and nitrogen are very electronegative elements, and so when they attach to the hydrogen, they denude that hydrogen, and the molecules can form hydrogen bonds as an intermolecular force. That's the main thing there. So they are anomalous. Of course, methane, carbon can't do that because it's not electronegative enough, and it also hasn't got any lone pairs, so it couldn't possibly do hydrogen bonding. And then this other part of the graph, well, this part here, well, this is interesting because it tells us probably that the van der Waals forces are more important than the dipole-dipole interactions. Okay.